tonight. It's more than Sunday night, right? So question 12, we have to figure out how, yeah, everything's a part. What a party here. Yeah, I'll go over question 11. I'm just going to start with question 12. All right. For this one to figure out what has the largest concentration of nitrate ions in solution, we have to figure out how it ionizes. So sodium nitrate ionizes 1-to-1, 1 sodium and 1 nitrate. So if I have 0.4 molar, I'm going to have 0.4 molar sodium and 0.4 molar nitrate. Whereas if I go and take a look here at the calcium nitrate, right? Calcium nitrate, when it ionizes, I'm going to get 1 calcium and I'm going to get 2 nitrates. I'm going to have twice the concentration of nitrate because of that subscript 2 tells me I'm going to have 2 nitrates for every calcium nitrate. So if I have 0.3 molar calcium nitrate, I'm going to have 0.3 molar calcium, but I'm going to have 0.6 molar nitrate. So that makes calcium nitrate, right? Choice C is going to be the highest concentration of nitrate in solution because when it ionizes, it's going to give you twice the concentration of nitrate in solution. All right. Now on to question 11. And we'll get to 13 too, as well. How many grams of the excess reagent? So salinity, this is a really hard problem. Question 11 is probably the hardest problem on the exam. You won't have a problem like this on your exam, but certainly it wouldn't be as involved in this, but it certainly could involve aspects of this. Like you'll definitely have a limiting reagent problem on the exam. You might have to find how many moles or the mass that's made from that. You're not going to have to do all of these steps. Like this would be 2 separate questions on the exam because it's too involved here for like a regular exam question. All right, so I've got 48 grams of aluminum and I've got 225 grams of iron 2 oxide. So MK went to the periodic table and looked up the molar masses of each of these for us. And so what do we have, MK, for our molar mass? Yeah, 26.98 grams for 1 mole of aluminum. And 1 mole of iron is, what, like 150 something? Yeah, 159.6. Because, right, I can't do anything with grams other than to find moles. So 48 divided by 26.98. I've got 1.77 moles of aluminum. 225 divided by 159.6. I've got 1.409 moles of the iron. Again, I can't do anything with this number directly because they're still not in the same unit. So I can't compare those as to finding limiting reagent yet. I want to convert them both to aluminum oxide so I can compare those numbers directly. So to do that, I go to the balanced chemical equation. That tells me I need 2 moles of aluminum for 1 mole of aluminum oxide. And here, iron to aluminum oxide is 1-to-1. So that one's not too hard. 1 mole of aluminum oxide for 1 mole of iron 3 oxide. So I multiply, I can make 1.409 moles of aluminum oxide based on the iron oxide in the reaction. And here I'm going to divide, so 1 point, enter, divide that by 2. Here I can only make 0.8895 moles of aluminum oxide. So we found our limiting reagent, right? The limiting reagent, right, in this case is aluminum, and that means our excess reagent is the iron oxide. Now let's go and answer A, and then we'll answer D, because I only need this information to answer A. Limiting reagent is aluminum. When aluminum's consumed, the reaction stops at 0.8895 moles of aluminum oxide. So for A, all I want to do is just convert moles of aluminum oxide into grams. Yeah, we want to find the moles of each of them, right? So here they're both in aluminum oxide, so I can compare those numbers directly to see which one makes the least amount of product. Aluminum made the least amount of aluminum oxide. So we can compare that at the step of moles. Here, they're asking for the grams of product as well, so we have to do one more step, right? 1 mole of aluminum oxide, MK tells us 101.96 grams. Right, so moles cancel out. We multiply by 101.96, and we're going to make like 90.7 grams of aluminum oxide, right, in this reaction. Now, to find out, right, the excess reagent, how much we had. So based on the iron oxide, we could make 1.409 moles of the aluminum oxide. That's how much we could make. We actually made 0.8895 moles of aluminum oxide. So we're going to subtract that amount because I could have made 1.4. I made 0.8895, right? That's how much I made. So that's why I can subtract what we made, right? So 1.409 minus 0.8895, right? I get a leftover moles, excess moles that I could have made of 0.5195 moles of aluminum oxide. We still need to convert that back to the reagent, back to the excess iron 3 oxide. So I've got 0.195 moles extra that I could have made. I didn't make it. I know for 1 mole of the aluminum oxide, right, this would convert back into 1 mole of the iron 3 oxide. So, okay, that means I'd also have an excess of 0.5195 moles of the iron 3 oxide. The last step, we want to just convert that into grams, right? I've got moles of the iron 3 oxide, and I know for 1 mole of the iron 3 oxide, right, way back up here, 159.6 grams. So multiply by 159.6, and I get like 82.9 grams. If you want to round that to 83 grams. Right, so Will asks, what would this question look like on the exam? This question would look like, basically, you're going to answer A. You know, if I gave you this many grams of aluminum and this many grams of iron 3 oxide, how many grams of aluminum oxide could you make? Or how many grams of iron could you make? So it would just be step A. Yeah, in the process to answer A, we had to figure out the limiting reagent in that case. Yeah, we would have to do B anyways, right, to figure that out. Yeah, excess minus limiting, and we have to convert it to grams. Yeah, and it is multiple choice. All right, there's 11, there's 12. 14 is up next. All right, okay. Sada would like to do 13. Yeah, I mean, the tutoring session, she had us take the grams of product that can be produced. Yeah. And then convert it into grams of excess and then subtract that from the starting amount. Well, we want to convert it from the starting amount of excess. We can't subtract on a gram level because they have a different molar mass, right? So you could subtract how much you could have made in grams from what you did make in grams. That difference you would have to turn into moles, and then you could subtract the moles, right? We can't do that on a mass basis. I honestly just, you can email the director of class or the associate director of class, like if you're having problems. I'm not saying that to take it like off of my plate, but like I don't hire the tutor. I don't have anything to do with the tutoring. So it's not anything in my control. So, all right, question 13. Here's another redox reaction for us, right? Here's rust, or actually, no, we're making iron. We're making iron, iron 3 oxide. All right. This one's kind of hard to see, but right, in iron 3 oxide, we're going in numerical order, Sam. We're on question 13, so it'll be a little bit until we get to 24. In iron 3 oxide, right, I've got 2 irons, I've got 3 oxygens. Oxygen's always -2, so that's -6 charge on the oxygen. The whole thing is neutral, so that means I need to have +6 from the iron. So iron needs to be 3+. So, okay, iron is 3+ here, oxygen's 2-. As a solid, right, iron is 0 over here. The other one is kind of hard to see because carbon monoxide, if I break down carbon monoxide, right, oxygen is always -2. It needs to be neutral. So that means carbon is +2 in carbon monoxide. In carbon dioxide, right, we have 2 oxygens now at -2 each, so that's -4. So that means carbon now needs to be 4+ to balance that out. So carbon here is 2+, oxygen's 2-, carbon here is 4+, oxygen is 2-. All right, so our oxidized species, like let's do the half reaction, right? I've got 2 irons at 3+, and they go to 2 iron at 0. The other one's harder to see. I've got 3 carbons at 2+, and that goes to 3 carbons at 4+. So to balance this out, yeah, 18 is up next after a few questions. To balance this out, right, conservation of charge, I've got +6 over here, and it needs to be neutral, so I need to add in 6 electrons here. I need some more space to do that. So +6 electrons to balance that out. And then over here, if I am 6+ here, and here I'm 12+, right, to balance that out, I would have to lose, right? Carbon goes from 2+ to 4+. It's going to do that by losing 2 electrons each, 2 electrons for each carbon. 2 times 3 is 6. So the oxidized species, right, oxidation is lost. So the oxidized species is the carbon monoxide. The reduced species, right, reduction is gained. That's going to be the Fe2O3.
CO got
Hey, do you mind muting yourself? I'll just do it for you. All right. So the oxidizing agent gets reduced, right? So that's the Fe2O3. The reducing agent, it gets oxidized. So that would just be the CO. Yeah, so answer Madison and Alexander's question at the same time, right? We need to balance charge. I need to balance charge. The only thing I have to balance charge are electrons, negatively charged electrons. So I looked, and before I added those electrons in, right, my total charge here, 2 times +3, my total charge is +6 on this side. My total charge here is neutral. The only thing I have to work with are negative electrons, right? Negatively charged electrons. So if I added in negatively charged electrons on the right, there's no way I can balance out this equation. So, okay, if I'm +6 here, but I need to be neutral, right? I can do that by adding in 6 negative electrons. Now +6 -6, that's neutral. There's at least going to be one acid-base question. All right. So we're good with this redox reaction now. And then so Madison, that's how I knew like what side to put the electrons on. So I'm trying to balance the charge. So here I'm 6+, over here I'm 12+. Again, I only have negative things to work with, negatively charged things to work with. We haven't even finished the redox reactions. So let's just pump the brakes on the acid-base questions here so I can just kind of answer the same questions. All right, so we're all set with the redox reaction. Yeah, iron shouldn't be an answer. Correct. Yeah. Even though, yeah, thank you, Ravi. Even though the iron got reduced, it was not elemental iron that got reduced. It was iron in the iron 3 oxide that got reduced, or that got yeah, reduced. It's the oxidizing agent, right? It's not the oxidizing species. What got oxidized is the carbon in carbon monoxide, right? This is reduction. Reduction is the gain of electrons, and this is oxidation. Oxidation is the loss. So carbon lost electrons, iron gained those electrons. Yeah, the
John?
species is the whole thing that's in the reaction, right? It's not just an element, right? And
I
the
had a
answer,
question.
thank you, Sophia. The answer should always be one of the reactants.
Nope.
Products, right, or the product of that. All right, question 14. Come on, question 14. Yeah, loss of
John?
oxidation. Yeah, it's balanced, right? 3 carbons. 3 times 2 is +6, right? 3 times 4 is +12.
I'm
6
sorry, Mr. John. I don't mean to interrupt you, but
I had a question. So for B and C, I put Fe2O3 like it said, and it said it's wrong.
Okay. Let me just see.
But
Yeah,
it's the
are
right
you
answer though.
using-
Because it showed me the explanation, and then I put it in exactly how it said to put it in, and it still said it's wrong.
All right, did you put like a 0 instead of an O for oxygen? That's the only thing I can think of, something like that.
No, I checked. I'm pretty sure I put O.
Because I'm looking at the answer right now, and it should be fine either
Yeah,
way.
it is the right answer, but I don't know why it said it was wrong to me.
I'm gonna guess you put in a 0 instead of oxygen,
Oh.
instead of an O for oxygen. Yeah.
Okay.
Or yeah, the case 2. Yeah, it doesn't matter. We don't need the coefficient. It's just the like what we actually used. Yeah. Because I've seen that before where someone uses 0 instead of
Take them to my
oxygen.
AirPod. You dead wrong. That's dead wrong. You know that.
All right, I don't know who that was. I just muted that. Right, it should just be carbon monoxide. We don't need that coefficient 3. And it tells you in the question, right? It tells you in the question, either use this, this, or this, or this. We don't need that coefficient there. Yeah. All right. Question 14 here, before we get too late into the night. All right, we got a 50-gram sample of each. They're heated. They're at 25 degrees. They're exposed to the same amount of heat. All right. So the sample that is the hottest sample, the sample that has the highest final temperature, should have the lowest heat capacity, right? They should take the least amount of energy to heat that up. So antimony, arsenic, barium, and beryllium. So this should have the lowest. And barium should have the highest heat capacity. So this should be specific heats from smallest. So this should be 1, that should be smallest, that should be next, that should be next, and then that should be last. Jack, I'm pretty sure I've approved all the requests I've received. I can go in and take a look again. I went in around noon today and approved every request that was in by noon. So all right, so to finish off question 14, right? We just want to put these in order, and yeah, I put these in order. So it should be SB is the lowest specific heat. Beryllium should be next, arsenic should be last or next, and then barium should have the highest specific heat. Yeah. Yeah, I think we did question 9 already. Right, because the lowest specific heat is going to take, because the lowest specific heat, right, the lowest value of specific heat. So let's just say the specific heat here is 0.1 joules per gram degrees Celsius, whereas the specific heat here is 5 joules per gram degrees Celsius. Right, that means if I give this 5 joules of energy, I raise the temperature 1 degree Celsius. Whereas here, if I give this one 5 joules of energy, I'm going to raise the temperature. What would that go in there? 50 times. So I'm going to go in, this is going to raise the temperature 50 degrees Celsius because it has a lower specific heat. So less energy is going to go farther, right? All right. Question. Yeah, I mean, all of these calorimetry questions, right? We'll do question 16 for our calorimetry question. And yeah, I'll get on to 20. I'll get some in the 20s, right? 16 is on the list. So I've got 73.1 grams of a metal. It's 115 degrees. I add it to a calorimeter at 19.5 degrees. The final temperature goes to 28.7. Specific heat of water. What is the specific heat of the metal? So we're going to do 2 calculations, right? Q for the water, MC delta T. So Q for the water equals my mass of water is 128.9 grams of water. The specific heat, 4.18 joules grams degrees Celsius. My delta T, I go from 19.5 to 28 degrees, 28.7. So what's that? 9.2 degrees Celsius. So Q for the water equals, right? The water absorbed this much energy.
John, did you subtract?
Yeah, right, to find our change in temperature, right? Final minus initial. Right, so my final temperature is 28.7 degrees minus 19.5 degrees. All right, so that gave us the 9.2. And then, yeah, how do I know when to use mass, right? Because our specific heat, right, has units of mass in it, right? It's joules per gram. So that's how I know I need to use this mass. Otherwise, the grams aren't going to cancel out. So it's going to be in the units, right? We need to track the units to know if we're going to use the mass or not, and the specific heat versus just the heat capacity, right? The other equation is Q for the calorimeter equals the heat capacity of the calorimeter times delta T. And there, the units are just joules per degree Celsius. So that's when we don't need the mass component, right? It's right there in the units that we're given. So heat for the water, 9.2 times 4.18 times 182.9. Right, I get like 7,000 joules of energy the water absorbed. So that means the Q for the metal, right? The metal lost that energy. The metal lost 7,033.6 joules of energy. Now I want to do Q for the metal, right? MC delta T. I know Q is minus 7,033.6 joules. The mass of the metal is 73.1 grams. I'm looking for the heat capacity and the delta T, correct. Right, the delta T, here it's final minus initial, so 28.7 minus 115.2 to get my change in temperature. So 28.7 minus 115.2, right? 86.5 degrees. So there, we're just going to multiply these two together. We divide across, so times 73.1. And then we've got minus 7,000 divided by that. And I get a heat capacity of about 1.11 joules per gram degree Celsius. They want the answer as we're looking for the heat capacity, right? Yeah, the sig figs, right? They want the answer as two significant figures because our change in temperature up here is two significant figures. So our final answer really should just be two significant figures. So 1.1 e to the 0 should be our specific heat for this metal. Yeah, the heat capacity for the water is given, right? Yeah. And then Madison, right? The water absorbed this energy. This is in the calorimeter. So the water absorbs this energy, which means the metal lost that energy. So we just flip the sign, right? It's the negative because no, we don't want to use negative Q divided by N because N is moles. We don't have moles of anything come from. It's C of S. It's our specific heat. I know, I'm sorry, my S's look like 3s when they're really small. Correct. The water absorbs. The water absorbs that energy. It needs to be a positive number because it's our specific heat, right? It's energy that's absorbed. So it can't be a negative number for heat capacity, right? I can't have a negative energy required to raise the temperature of something. So it should be positive because this negative gets canceled out with this negative here. Yeah. All right. I'm not gonna do question 15 because it's just, Q equals MC delta T, right? There's our Q, there's our M, and there's our delta T. So it's just multiplying, yeah. Right, this is our heat capacity. That's telling us how much energy is required to heat this per gram per degree Celsius. And it's two significant figures because 9.2 degrees is two significant figures, right? All right, question 18. Oh yeah, question 18 is a good one. All right, question 18. They want to know how to precipitate. How can we figure out what's in solution? I've got silver nitrate, calcium chloride, and aluminum sulfate, and I want to choose this. Right, so if I add sodium chloride, I basically want to use that solubility table. If I add sodium chloride or potassium bromide, the only thing I can precipitate would be silver chloride. That's the only product that we could make. All right, what was question 17? Balance the chemical reagent. Yeah, it's just balancing the chemical reagent. 17 should be pretty straightforward. So if for 18, if I have sodium chloride, potassium bromide, I add this. The only thing I could precipitate is silver chloride. So that wouldn't help me. If I added iron nitrate, right, nothing with nitrate precipitates. So this is not going to determine anything is there, right? Nothing's going to precipitate based on. All right, can we just calm down in the chat? I don't know what we're worked up over here. Right, iron nitrate, the nitrate's not going to precipitate anything from the reaction. Sodium won't, iron won't either, so that doesn't help us. All right, the barium nitrate, when I add that, one of the possible products I could make is barium sulfate. That's a solid. So if I added that, right, that would precipitate if aluminum sulfate was in the solution. When I add sodium chloride, because chloride's present, a possible product could be the silver chloride. That would precipitate when that's in solution. So if I added the barium and nothing precipitated, I know aluminum's not there. If I added the sodium chloride and nothing precipitated, I know that the silver's not there. And by default, I would know it's calcium chloride. Or if in this process I added the barium and I got to precipitate, I know it needs to be barium sulfate and the unknown should be aluminum sulfate. Or if I add the sodium chloride in the precipitate forms, I know it must be the silver chloride, so the silver nitrate is there. So yeah, you would just use the solubility table. I didn't have it here to like paste it into the question. And correct, they're solid because they are insoluble, right? Barium sulfate is insoluble. Silver chloride is insoluble. All right. So much for me.